Consider the origin O in a plane. We define a relation between 2 points P and Q such that OP equals to OQ. Prove that this relation is an equivalence relation. Okay, let us begin. We'll first try to understand the problem graphically. So what we have here is the Cartesian coordinate plane, the x-axis and the y-axis intersecting at O. So O is going to be the origin. And we are going to consider 2 points P and Q on this plane, on this Cartesian plane. So let's say P and Q be 2 points on the plane. So let's join point OP and OQ. Now, the position of point P and point Q on this coordinate plane is chosen in such a way such that the distance OP is going to be exactly the same as the distance OQ. That means the length of OP and OQ are equal to each other. Now we have to show that this is an equivalence relation. So let's do one thing. Let's first define the relation R. The relation R, this is going to be a set of ordered pairs. So the ordered pairs is going to be OP, OQ, such that there must be a relationship between these two elements within the ordered pair, OP and OQ. So the relation is such that we have OP equals to OQ. Fine. And both P and Q are 2 points lying on the plane. Right. So this is our relation. Our goal will be to show that this is an equivalence relation. Okay, let's start by first checking out whether if this is a reflexive relation or not. Because the moment we are given in a problem to show that our relation is an equivalence relation, our goal will be to check whether if that relation is reflexive, symmetric and transitive or not. If it fulfills the criteria of being all three of them, then we can immediately say it is an equivalence relation. So we'll start with the reflexive relation. A relation R is which is defined on the set A is going to be reflexive in nature if and only if the ordered pair A, A belongs to the relation R for all values of A belonging to the set A. So here what we'll do, we're going to choose an arbitrary point on the plane. So let P be the arbitrary point on the plane such that if we consider the ordered pair OP, then the second element in that ordered pair must also be OP. Such OP, this belongs to the relation R, would simply imply that OP, because we have the relationship between the two elements of the ordered pair as OP equals to OQ. Since we have both of them as OP, so we'll write OP equals to OP. Is this a true statement? Yes, that's definitely a true statement. The line OP is definitely going to be equal to itself. This is being a true statement. Simply tells us that our relation R is reflexive in nature. This is a reflexive relation. Fine. Okay, so we have proved the first part. That means our relation R is reflexive. We go to the next one where we'll show that the given relation R is symmetric as well. Now, to check for symmetry, what we'll do, we'll consider an ordered pair A, B belonging to the relation R. This would imply that B, A also belongs to R for all A and B belonging to the set A. Now, in our case, what we'll do, we're going to consider 2 points. So let P and Q be 2 arbitrary points picked up from the plane, such that if we consider the ordered pair OP, OQ belonging to the relation R, so we have the relation R defined here. This simply means that OP equals to OQ. This is the relationship between OP and OQ. We're saying that the length OP equals to length OQ. Now, we can also say that OQ equals to OP. In other words, what we are saying, if OP equals to OQ, that would simply mean that OQ must also be equals to OP. In other words, what we are saying here, that means the ordered pair OQ, OP, this must belong to the relation R. Now this satisfies the criterion of being of the relation being symmetric. So we can say, so our given relation R is symmetric. This is a symmetric relation. Fine. And now we will finally come to the third one, where we'll check whether if the relation R is transitive or not. Now, R is a relation on the set A. Then this relation R is going to be transitive if we consider the ordered pair A, B belonging to the relation R and another ordered pair B, C belonging to the relation R. That same relation R would imply that A, C belongs to the relation R for all values of A, B and C picked up from that set A. So this is what it means when we say that a given relation R is transitive. So in our case, what we'll do, where we already have 2 points P and Q, we're going to consider a third point. So let's say the third point is S. Right? So we have the third point S such that if we join point O and S, we're going to get another line OS. So let us begin our proof. We're going to consider 3 points. So let 3 points be P, Q, and S. So let P, Q, and S be 3 arbitrary points, such that if we consider the ordered pair OP, OQ belonging to the relation R, and we're going to choose another ordered pair OQ, OS belonging to the relation R. What does it mean? So OP, OQ belonging to a relation R simply means that OP equals to OQ. That's already defined in the relation R. And we have another ordered pair OQ, OS belonging to the relation R. That tells us that OQ must be equals to OS. That is the definition. Now OP equals to OQ and OQ equals to OS. Can we not say that OP must be also equals to OS as well? Now if OP equals to OS, this is simply telling us that the ordered pair OP, OS belongs to the relation R as well. So here what we have done, we consider two ordered pair OP and OQ, OP, OQ as well as OQ, OS, both belonging to the relation R, and we were able to show that OP, OS also belongs to the relation R. In other words, we have shown here that R is transitive as well. Our relation is transitive as well. Now we can finally say that since our given relation is reflexive, it is symmetric, and it is transitive, so we can say hence our relation R is an equivalence relation. It is an equivalence relation, and equivalence relation, hence proved.